Going. Good. Let me just apologize. I had a little bit of flu difficulty left over from a horrible weekend, and but feeling a bit better today. Still a little bit pokey, but we're making it. And I was not thinking I should, and I know that this is the last class and sometimes the only class of the day for many of you on campus, and I ought to have sent out an alert through messaging or even an announcement on the website to save you guys the difficulty. And I understand Darian told me that several of you mentioned it, and I should have thought of that. I was kind of I was hoping to come to campus, but it just was not going to come together. So, but next time, if there is a next time, I'll try to alert you electronically a little bit more efficiently. And for those of you that did come, I'm glad you did come. And unfortunately, Miss Darian didn't have the clicker system, so I couldn't take attendance of the people the diehards that did come to class. We could have done a little clicker question and taken attendance, but we didn't do that, so maybe next time. We had to do that a lot during fall semester. You guys were here for fall semester, so you know. That was amazing. 2 weeks of school, basically. Gone. Erased from existence. I hope to never go through that again. All right, we're going to do some participation grade examples. I want you to take some notes on this so that you can do your own participation pointage yourself at some point. At any point that I publish a new roundup figure. And I did publish a roundup score yesterday. Here's what it looks like. There's something, I want you to look at this carefully. There's something on this that I need to explain. A few of you have messaged me about it, but I'll try to explain it to everyone now, and it will be on the podcast. Over here, let's see if we can get my cursor over here. Here we go. All right, right here it says 30.3. Now, on my spreadsheet, it's, this is not the way this is what I have on the spreadsheet, 30.30. All right, if you guys know anything about Excel or numbers on a Mac, you can format, to any number of decimal points that you need. All right, now we need those 2 decimal points to communicate the number of questions that you've answered correctly. Now, and web's courses, if there's a 0 in the 100th place or further out, if the last decimal place, whatever it is a 0, it won't display it. All right, so if you have a score, like right now, there are 30 questions on the books. Okay, so if you've answered 25 and you've gotten 20 correct, it'll read like 25.2. It won't say 25.20. Right? So if you ever see something that just looks like 2 or 1 or something like that, anything like this one says 30.3, just know that there's a 0 that's supposed to be there, but Web Courses does not allow me to display it. It's either Canvas's way or the highway. And I apologize. Well, I'm not going to apologize for Canvas, but I'm going to just alert you that Canvas is not being very cooperative. Now, I said we'd go through some examples, start taking notes now. As I said, right now, as of last Thursday, there were 30 questions on the books in lecture. Now, this is not counting exams. This is just regular lectures. All right, and what we have to do is convert your participation percentage which could be 73% or some other figure, and convert that into 25 points possible. All right. And right now, the criterion for full pointage for the whole semester is 85% participation. And this is why I always say, if you miss a lecture, don't sweat it. All right. If you miss 2 lectures, you're probably okay. You could probably still come in at 85% or higher. But if you miss more than 2, you're probably going to decrease your participation pointage because you won't have 85% of the questions answered. As I always say, there's usually 1 or 2 lectures to burn. So like we had a student this morning in my astronomy class. Her clicker answered the first question and then it failed because she had a used iClicker and the batteries were, flotacious. So they failed on her right after the first question. All right, so that happens. Or another student on the exam, I know last week we had a few people without it. Their roommate had it or something like that. All that stuff happens, I know. And so to give you a little bit of leeway, I always insist, 85% is going to get you full pointage. All right? And here's another example I just thought of this morning. You go to the store, Publix or Walmart or something to buy groceries, and they have, if you ever do any shopping, they have, sometimes buy one, get one free. Well, our participation pointage is like that. It's not buy one, get one free. That'd be 50%. For us, you pay 85%, you get 100% of the 25 out of 25. All right, so right now, 30 points, 85% of that is 25.5 approximately. So we have to go by a whole number of answers. So if you have 26 or more in the grade book, that means automatically you get 25 out of 25. No, just ding, you got it. All right, you get 27, 28, 29, 30, ding. No questions about it. It's only if you're below 25% or below 85% that we got to do a little calculation, a little bit of fancy footwork. And we're going to do an example. First example, though, is Justin Bieber, which so many people admire. Let's say that he's in class and he has 27 answers. All right? Now, that's 90%. All right? So are you making notes? You should. This might be you. Well, I take that back. I don't mean that you're like Justin Bieber, but you might have a score like 90%. All right? And that's above 85%. So that means that JB gets 25 out of 25 on his semester grade. So that's the easy one. Right? So, and you'll always be able to tell when I publish a roundup. You look in the whole number part, that tells you how many answers you got. All right? So he might have 27.22. Right? Yeah, that means he has 22 correct, but 27 answered. 90%, above 85%, ding, he's squared away. All right? Now the tricky part, we're going to do John Q. student now, is if you're below 85%. So this is where I seriously want you to take notes. So we're going to say that we've got some student, even if he's from outer space, a robot or something like this, from Futurama. And let's say that he has 19 answers. Okay, so Bender is he's participating, but he has an attitude, and he only gets in 19 answers. All right, and that's below 85%. It's below 26. All right, so that means you got to go to the proportion. All right, now this is what I want you to write down. Okay, this is the proportion that you've got to calculate at any point in the semester that you want to know what your pointage is. All right, so John Q. student, his pointage is going to be the numerator on the right side of this proportion. Now, this is also in the syllabus, And we're now going to work at this example, as I promised, on the first and second day of lecture. All right? So, first thing you do is calculate your answers percentage. So for a John Q student, that's 19 out of 30, right? And that's 63.3%. Can somebody verify me on that? Is that correct? 19 out of 30 is 63. Better get your calculators out and your clickers, because you're going to be doing this calculation in just a minute on iClickers. All right? So just get your calculators ready. All right, so now that goes in the numerator, 0.633, and then 0.85 in the bottom. Now you divide those out. All right, so the left-hand side is, when you calculate that out, you divide by 0.85, 85%, you get 0.745. All right, that's the quotient on the left for this example. Now, every time I post a roundup, you're going to have a new total. So right now the total is 30. You're going to have a number somewhere between 0 and 30, depending on how many questions you've answered. All right, so the next one might be 48. And the next time I do a roundup, because we're going to be doing clicker questions today, so it's going to be bigger than 30, and it might be 48 by the time I do another roundup. All right, but whatever it is, you calculate the percentage, then divide by 0.85. And then what you do is you cross multiply by 25. All right, and in this case, can somebody verify me on that? 25 times 0.745, is that 18.625? Is that 627? Okay, so it may differ out there, but it's 16 point something. 16.6 something. Oh, sorry, I misread it. 18.62 something. All right? Now, as always, and make sure you do this, and make sure you're aware of this, on homework and on clicking participation, I always round up. Now, this one would round up anyways. So if you showed this number to one of those guys in the math department that are always on your case, like the people that come in after this, that's a math class, I think, they would say, all right, that rounds up to 19 anyways. But if some other combination of numbers, if it came in as 18.14, for instance, so, some other, later in the semester, 18.14, you'd get 19 points for that as well. All right, so this particular student would have 19 out of 25 on their semester grade. All right, now we're going to try a participation calculation on iClicker in just a second. But before we do that, I want to pause for questions. Yes?
What was the percentage of answered questions correctly that would give you the bonus point?
Okay, the question, well, that's extraneous to our topic today, but the question was, at what percentage level do you get bonus points at the end of the semester? The second part of your roundup score, the hundredths part, those 2 decimal points, that tells you that encodes how many you've gotten correct. All right, so what you want to do there is you want to get 75% or higher. In other words, get a B on all the clicker questions of the semester, and then you get 4 bonus points. Okay, it's a nice chunk of change. All right, so that's that. Another question. Okay, I guess you guys are geniuses, so let's do the iClicker item. J. Jonah Jameson, Peter Parker's nemesis, and his boss. All right, so April 31st, the number of questions on the books is 48. J. Jonah Jameson has 35. Does he get automatically 25 out of 25? Go ahead and answer this. There's 2 yeses, there's 2 nos. So not only do you have to decide the correct yes or the correct no, but you have to distinguish between 2 versions of yes and 2 versions of no. I see somebody over here on the other side, on the left side of the room. He's got his clicker over here and his calculator over here, calculating wildly. Very good. It's lovely to see. Definitely consult with your neighbor too, if you're a little bit nervous about it. I'll give you 20 seconds to vote. Dare, you want to grade this one? This thing is, it's burning my grits. Good. How does that?
I don't know.
Sometimes it works, sometimes it doesn't. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, dear.
Oh, sorry.
Okay, 80% of you answered correctly. And here's the, if you missed it, the answer is no, because his participation percentage is 72.9, 0.729, that quotient, and that's below 0.85. So no, he does not get 25 out of 25. But he does get some points. Let's calculate how many points J. Jonah Jameson does get, and then we'll fire him. He fires Peter Parker every 5 minutes. This is numeric. So hit the refresh key on your on your clicker, and then you'll have a numeric answer. So and on this one, this is the proportion. Okay, so use your proportion. No clicker today? Oh man, what happened? Somebody else has got it? Somebody else has got your clicker? It happens. Yeah, so consult with your neighbor and just double check, re-verify and stuff like that. I'll give you a minute to do it. But make sure you hit the refresh key. What are you doing over there? Texting somebody. Fine. I thought you were working hard over there on something.
Dr. I'm too tired to work hard on anything.
Oh, brother. Okay. I know what that is. Yeah. It's out of 48, so it's a little bit later in the semester. Okay. Right now we got 30, but eventually, what we'll have? We'll have 48. We'll probably be up close to 100 by the end of the semester. So that baseline number, the number of questions asked will change. It'll be different every time I publish a roundup. So type in your answer to the nearest whole number, and don't forget to round up. And then hit the send key. Question.
Are we calculating the percentage or the actual points out?
You're calculating the pointage
Out of 25?
out of 25. All right. Question.
I want to make sure, so no matter what decimal place is on there, even if it's 0.1, you round up?
If you have, 11.00001, 12, ding. Yeah, it just, it saves a lot of heartache and stuff and mental commotion. Question.
Out of 48 or 25?
It's out of 48. The number of questions as of April 31st is, yeah. So it's, in other words, it's later in the semester. So, between, here and there, it's, this mythical semester, we've got 48 questions on the books. Actually, April 30, oh, wait a minute. There's no April 31st this year. right? There's no April 31st this year, or any other year. So you know this is a fictional example. All right. So here's your question. All right, 30 seconds to complete your answer starting now. J. Jonah Jameson. Have you ever seen anybody that goes to, you know, nearest to the round up to a whole number? Yeah, yeah. Have you ever seen anybody go to Comic-Con with as J. Jonah Jameson? No. What do you go as?
What?
You dress up, right?
Oh, I've never actually gotten to go to a Comic-Con. Yeah. It's okay. I might go this year.
Seriously? Yeah. What would you dress up as?
I don't know. I haven't figured it out yet.
Yeah. Katie. Yeah, you're converting to some number out of 25. So you calculate the left side, then you cross multiply by 25.
I'm confused. Is it out of 25 or is it out of 48?
There's 48 questions, and we're converting to something out of 25 for the semester grade. Yeah. All right. Oh, you got to re-enter your answer?
Yeah.
All
It's
right.
the third time I re-entered.
Yeah. That's all right. You change your mind. Katie, you got it? Yeah. Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And let's go through the calculation. We're going to display this in a minute. So here's the calculation. All right. His participation percentage, we already calculated, 72.9%. So the quotient on the left is 0.729 divided by 0.85. All right. And the 48 doesn't even come into it anymore. Once you get that percentage, 72.9, they forget about the 48. All right. Now you cross multiply by 25. All right, so this is a slightly different look. All right, you form your this is slightly different from the way I just did it before with John Q. Student. All right, with Bender, but you know you can keep your quotient intact and park your 25 over to the left. By cross multiplication if you want. But eventually you got to calculate your quotient. Right? And when you do, you get 0.8576. You multiply that by 25 and you get J. Jonah Jameson's pointage. Okay, so 21.44, all right? That's below 0.5, but you still round up. So J. Jonah Jameson gets 22 out of 25 on his semester grade. All right, now I want you to look at some of these answers. Derek, can you display this? And let's go ahead and mark.
I don't get the 25 part.
In our semester grading scheme, all of our participation is converted to 25 points. So every exam is 50, so you have some number out of 50.
Right.
The final is 100 points, so you're going to have some number out of 100. Now, clicking is a little different, but we're converting it so that it's half the size of a midterm.
Okay.
All right, so you're going to get some number between 0 and 25 out of 25.
So,
right? And so that's what we're doing here.
25.
What's that?
For clicking, always is 25.
Yeah, clicking always converts to 25, and homework also converts to 25, but you don't have it, you just go straight percentage with homework.
Okay.
All right, so you take whatever your performance percentage is for homework, multiply by 25 and round up. This one, you got to go with that proportion.
I multiplied by 48.
Yeah.
I did everything else right. It was
Yeah,
just-
so now, Darian, can you scroll through some of these answers? 22 is the right answer up at the top. I don't know how you get, hold on, let's look at 19. I don't know how you get 19.
19, you take 0.729 and times it by 25.
Yeah.
We didn't.
Oh, 0.729, yeah, so that, okay, so that's an error. 21, you rounded the wrong way. You forgot to round up, even though I told you to round up. 73, that's a whole number percentage for 72.9. 18, I don't know what that is. 35, 85. All right, let's go back to regular display. You can see that, anyways, what I want you to do is make sure that you're, and we could, you know, if you're unsure yourself, you know, you can double check with me. But I want you to try, next time you want to figure out your grade, I want you to be able to do it this way. Right? So no matter what you're doing, at any point in the semester, when I publish a new roundup, you'll be ready for it. All right? It'll just be the same way. Right? And just go back to this lecture. This is lecture 12. All right? Go back to lecture 12 and try to repeat the calculation. All right, Sadie? So that's how you do it. All right, now let's keep going. I want to talk about uniform circular motion. This is actually the tail end of chapter 3, around page 38, I think. And what we're going to talk about is something called the Nardo ring. And it is a test track for motor vehicles in Italy, down in the boot heel of Italy. Here it is, Nardo. And it's just a great big circular track, and it's going to be our concrete example of circular motion. And what they do is they just they take a vehicle that they've designed and they run it for hours and hours on that track, and to see if you know, how the engine holds up, how the suspension holds up, all that kind of stuff. All right, so here's the close-up. The radius is about 2,000 meters, depending on which lane that you take. Here's getting a little closer here. Here's an overhead view. Okay, and so let's talk about this. The outermost lane, the optimal speed is 149 miles per hour. All right, and if you're at that speed, so this is like for sports cars, you know, like Ferraris. You know, so they, you know, the Lamborghini company probably uses it, Mercedes and, you know, Audi, and, you know, for a circular ring, this is what they use, Fiat. All right, and if you're going at about 149 miles an hour, you're good. If you want to go faster, you have to crank the steering wheel a little bit, a few degrees to the left. I believe they go around a counterclockwise manner. Right now they have another ring that's configured for trucks. It's banked a little bit differently, and so 50 miles an hour is the optimal speed. Probably passenger cars too, you know, regular civilian vehicles. So trucks and, you know, faster than 50 on that track, you have to crank the steering wheel a few degrees. All right, and so and you can see this is the view from space. It's pretty ginormous. All right, so what we're going to do now is rederive those equations of motion for a simple circular path at constant speed, in other words, uniform circular motion, and we're going to reinforce the geometry of it. So this is what we looked at basically last time. An object on a circular path at uniform speed, so uniform circular motion, at two different times, and I have them swung at about 30 degrees apart here. So time t1 and time t2, it's a little bit further along. But the velocity vector v, that red arrow, is the same size. Now it's tilted in a different direction. It's tilted a little bit, it's tilted like, I think it's 30 degrees to the left of the arrow at time t1. Time t1, it's straight up. Time t2, it's tilted a little bit left of straight up by about 30 degrees. And the same direction that the position vector here is tilted 30 degrees to the left of where it was. Right? So the position vector, this first radius, r here, is horizontal. Okay, so the velocity there is perpendicular to that. So the velocity is straight up. Okay, it's tangential to the path. All right, and it's straight up. And the location radius, the position radius, is straight across. It's horizontal. All right, so they form a right angle. Now, they form a right angle up here, so if the position changes by 30, the velocity vector changes by the same 30 to the left. All right, so that's what we got here. All right, now we're going to do a little bit of rearrangement here. Okay, what I'm going to do is move my two position vectors. I'm going to copy and kind of park my position vectors down here to the lower left. All right, and then I'm going to copy my velocity vectors. There's the copy. All right, and I put them tail to tail, and see, there's the copy, and I'm going to park it up here to the upper right. You know, just so it's out there, so we have some room to roam and, you know, keep the notation clear. All right, now let me park these things up to the side and make my two vector sets a little bit differently. By the way, a vector is the word that we use for any physical quantity that can be represented by an arrow that has a length and a direction. All right, so here are my two vector sets, and go down to the position vectors, tail to tail, and draw a dotted line from tip to tip. All right, you know, the initial one is flat. You know, here's the shrink down of it. This is T1 up here, and here's that same position vector at time T1. It's just a little bit bigger. And then here's the position vector black up here. It's about 2 o'clock. Right? So here it is down here, 2 o'clock. Now, I didn't draw it in up here in the two circle diagrams, but I do want you to draw in the line and form a triangle here. All right? Now, we're going to do something about this, but before we do that, let's put in R and R, same size. Hey, what kind of triangle is that called? Yep, an isosceles. Okay, remember that from high school geometry class? All right, so now that dashed line for the position triangle is the approximate distance. All right, now that's as if a crow were flying from the tip of one arrow to the tip of the other. All right, but it's not a crow, it's on a circular path. Right, so this is approximate. You know, the true distance would be the arc that connects those 2 points. But we're going to approximate the arc by this straight line. It's pretty close. All right. Now, let's do the same thing up here. The two velocity vectors up there, let's connect the tips of those two babies. Now, they're oriented a little, you know, one of them straight up and down. That's the velocity vector at time t1. That's this one over here, right, on the far left. And then this other velocity arrow here in the upper right, this one is tilted a little bit to the left. That's this velocity vector at time t1, or excuse me, at time t2, all right? Now, this is also an isosceles triangle. Now, what would you call the dashed line between the two velocity vectors? If you did any reading, you know the answer to this. That, my wonderful students, is called delta V. This is the change in the velocity. You know, from the initial to the final. From velocity 1 to velocity 2. All right? And we could give that an arrowhead, but I didn't put one in here. All right? Now, here's the kicker. These are both isosceles. The other thing that's true about these, whatever this angle is down here for the position, the sharp angle for the position triangle, this sharp angle for the velocity triangle is the same size. If it's uniform circular motion, those two angles, 30 degrees, 2 degrees, whatever number of degrees, it'll be the same. Right? So mark down that you have isosceles triangles and that the peak angle, the sharp angle, is the same for both. So the sides are proportional. So the two triangles are similar. You know, you can't say that they're congruent to each other because one is measured in meters, the position triangle, and one is measured in meters per second. That's the velocity triangle. So you can't say that they're congruent, but you can say that they're proportional. Right? So you can do proportions with them and stuff like that. And that's what we're going to do. Now, one more important thing that we have to do. This approximate distance for the position, the base of the isosceles position triangle, it's approximately delta x. That is approximately v delta t. However fast you're going times however much time elapsed. So t2 minus t1, that's delta t. Right, so v delta t, so that's speed times time. Right? And it's a straight line segment, that's as a crow flies. As the car moves on a circle. But if you make your angle smaller and smaller, you know, it gets closer and closer to the distance of the arc, so everything's good. Now let me clear these big yellow things out of the way. And here's the first proportion that we're going to use. I said that the two triangles are similar. Yeah. And because that is true, you can make a proportion. Now, this equation up here, it's a proportion, R over V. And then on the right-hand side, it's V delta T over delta V. All right? Now, you may say to yourself, Dr. B, how did you get that? Right? Well, here's how I got it. This quotient here, R over V, that's the ratio of the isosceles sides. Right? So you take the two long isosceles, one from the position triangle, one from the velocity triangle, and you make a quotient of it. Right? So it's position triangle over speed triangle. Right? And then over here, this part, this is the base of the isosceles triangle. All right, so this is the dotted line. So position, triangle, dotted line in the numerator. And then down here in the denominator on the right, the dashed line of the velocity triangle, delta V. All right. Now, I want you to look at those two proportions now. Look at them carefully. You see anything in there interesting? It may be kind of cloaked. It might be rearranged, but you might be able to see. What do you see? Anybody see anything? What do you see? What's inverse? You know, it's a good idea, inverse. That means one quotient is a flip-flop of another quotient. But I'm just saying in this, you know, and we could we could flip-flop this whole thing, you know, and then it would be velocity triangle quantities on top and position triangle quantities on the bottom. But anything else that you notice? Look carefully and think. Is there anything there that you've seen or kind of seen? What do you, can the V's cancel? No. But I'm glad you brought that up because the V's, it's important. Go ahead and make a note. The V's do not cancel. Nothing cancels here. There's nothing here that can cancel. Right? So we're gonna be stuck with the V's. That's important. Right? We got the V's, they're gonna stick around for a while. Anybody else notice anything? We've got R's, we got a factor of R in there, but it doesn't cancel with another R, so it's, you know, it's gonna stay. Anything else in there? Look carefully and think. Okay, you guys over here. What do you see? What are you pointing at? Come on, be crazy. What do you see? The V's? No, they don't. Yeah, we're not getting rid of them. Because one's on the denominator of one side, the other's on the numerator of the other side. So that means you cross multiply and they stick together. You're going to have a V squared coming out of this. Let me ask you a question. What's the definition of acceleration? What over what? Remember that? What over? Raise your hand if you remember. Definition of acceleration. What is it? No? Definition of, what is it? Delta V over delta. You see any delta V's over delta T's in here? It's not the opposite. What do you see? You see it? But it's not delta V over delta T. It's the inverse. You see it? Right here. Delta T over delta V. Hey, that's an acceleration in the denominator. All right? So let's rearrange this now. Here we go. There's a little bit of and then we've got V squared. And now we've cross-multiplied delta V to the top on the left, delta T to the bottom on the left, and we cross-multiplied a V to the top of the right, so now we have V squared over there. And we cross-multiplied the R to the bottom on the right, so that's in the denominator, all right? And that, my wonderful students, is why the formula for centripetal acceleration is V squared over R, which we talked about last week. So let's do a visual summary now. Yep. You construct the position triangles at any angle you like. You construct the velocity triangles that correspond, and that's going to be a similar triangle. Because the similar triangles create a proportion, you can make that proportion. Now, up there in the upper left, that's geometry class with physics symbols in there. But this, down here in the bottom, that's Sir Isaac Newton talking. He's the one that figured this out. V squared over R. Right? So that's the chain of logic. The V squared, it came Here's a V, cross multiply to the top. This V is already on the top. The delta t goes to the denominator over here. Delta V goes to the numerator over here. And I got this R over here. I'll park it on the bottom over here. And that gets me this. So we're just rearranging the furniture a little bit. Okay, now here's a summary. Go ahead and make a circle with one radius from the center out to, and mine is out there at 3 o'clock. All right, and I got a tennis ball. Oops, here we go. I got a tennis ball there at 3 o'clock. The centripetal acceleration is directly aimed at the center. That's why we call it centripetal. That means toward the center. Centrifugal means away, fugitive of this. It's fuging away from the center. So that's not what this one's doing. It's going toward the center. So we call it centripetal. All right, and that's the blue arrow there. The velocity is, so this is like T1. And now at T1, we've also got the acceleration vector. Now that's really important. Here's the position vector R. Right? And now if you're on a circular track, you've got to have some grip force from your tires. You don't want to have bald tires out there on the Nardo ring. Well, you could do it if you're going 2 miles an hour. But if you're going 149, you better have some pretty good tires. They've got to provide some force, otherwise you'll slide off the thing and you'll crash. You don't want to do that. So you can have some, and that's going to produce some F equals ma. The A is this one right here. All right, now you control that with, for instance, the gas pedal and the brakes controls the speed. And then the design of the track is set, 2,000 meters or whatever it happens to be, whatever the track is that you're on. And so that's how you control, if you want to have a certain centripetal acceleration, you've got to have good tires, you've got to have the right speed, and the size of the track is set. All right, now, here's the logic behind it. Because of proportional triangles, the speed triangle being proportional to the position triangle, we get this. And then, of course, the centripetal force is just m, the mass of the car, times that. So that's mv squared over r. And actually, that last one is going to be important for us in the Newton's theory of universal gravitation. All right, so go ahead and write down centripetal force F subscript C equals mv squared over r. And you can write it either way. It's basically F equals ma. So whether you're a car going around a circular ring, or if you're the moon going around a circular orbit, whatever your speed is, square it, divide by the radius, and that'll tell you how many meters per second squared of acceleration you've got to have. All right? Now, the guy that leveraged all this into a theory of universal gravitation is Sir Isaac Newton. All right? And that's what we're going to talk about now. And before we get to the notes about that, I want to make you aware that I have written a new chapter, kind of a mini chapter for your ebook, and it is in web courses. It's called Gravitation MiniChapter G. Okay, so it doesn't have a number; it's got a letter. MiniChapter G, and if you look on the homepage, there's now a page that says free chapters. Okay, so click on that, and you'll be able to download it as an EPUB format, and you'll be able to read it in a ebook reader, Kindle or whatever you've got, a Nook, etc., etc. iBooks, that's what I use. So it looks like that. And there's a bunch of diagrams and stuff in there. It's pretty good. Now we're going to go over some of the concepts in that chapter right now. And as I said, uniform circular motion is important because of how Newton developed his theory of gravity, he basically said that the force of gravity, in his theory, it depends on two physical factors: the mass of the object, in other words, the quantity of inertia, the measurable quantity that corresponds to inertia, in other words, how many kilograms. And then he said that it depends on the distance. Now, the reason that he felt that is because of, and you can read about in MiniChapter G. So, in other words, the two physical factors mean this: if your object has more mass, more kilograms of mass, then it'll provide or generate a stronger force. Right? If there's more distance between the two objects, then the force gets weaker. Right? And there's a formula that Newton developed based on some astronomical and other observations that he and others had made over the years from the time of Galileo forward, that he figured that, the force that controls the free fall of an apple out of an apple tree is the same force that controls the orbit of the moon. Now, the way that he explained it, or one of the ways that he explained it, was he thought of the moon and he thought of the moon, and he said, think about taking the moon and just dropping it straight down toward the earth. And and you can read about it in MiniChapter G. He thought a lot about the moon, and you know what else he thought about? The moons of Jupiter, which Galileo discovered, and which by the time Newton was developing his theory, they'd measured them very carefully, how their orbital period, the orbital distances, all that stuff. All right, so this is the force law that he came up with. And you can read more about it in MiniChapter G. The distance r between two objects. The two objects each have a mass, m1 and m2. And the distance between the objects, Alexis, is r. Okay? So that goes in the denominator. And it's not just r. It's r squared. Now, I'm going to give you some concepts here about this. It's known as an inverse r squared force. Inverse r squared force. In other words, the r squared is in the denominator of the force law. As Newton would say, inversely proportional to the squares of the distance. That's how he worked it out. But this is the force law, r squared. And so make a note, it is not r to the third. It is not r to the first power. It's not r to the 1.5 power. It's not r to the 3.2 power. It's not r to the 2.001 power. It is exactly r to the second power. And believe it or not, we have actually measured that exponent. There's ways to set up an experiment to measure that exponent. Is it 2 or is it something else? And right now, we are convinced that it is exactly 2, as far as we can tell. And that is important because any force that is r to the second, inverse r to the second power, has infinite range. Let me repeat that. Any inverse r squared force has infinite range. And that is another reason it is called universal. Every atom and molecule in your left earlobe is being attracted by the moon. And then the moon is being attracted by every molecule in your left earlobe. And the most distant galaxy, billions of light years away, is being attracted just slightly to your left earlobe. And your right earlobe. And every other, your little toe. And your little brother's little toe. Your stinky little brother's little toe. All right? And everybody, and everybody that you know, their little toe, and their nose, and every hair on their head, everything. Everything is in mutual interaction. Now, second note. Because the universal gravitation law depends on the mass, Earth has the lion's share of the dynamical effect on each of us. Okay? Every single one of you is being gravitationally attracted to my big head. But it doesn't feel it very much. You don't really notice it. But you do notice every one of you, every part of your body is being attracted straight down towards the center of the earth. All right? The center of mass of the earth. And so the mass of the object, if it's really big and you're really small, the big object is going to create a big force on you, and you're going to get a decent sized acceleration, 9.8 meters per second squared. But you're not going to, you're not producing any big acceleration on the Earth. I mean, you could calculate it, but it's not very big. Because the mass of the Earth, the F equals ma for the Earth, the mass of the Earth is ginormous compared to you. But your mass is not ginormous, it's minuscule. So the acceleration, you get the acceleration. Everybody, you and the Earth get the same size force, action and reaction, but you're the only one that has observable amount of acceleration. And the same with the moon. The moon moves the Earth a little bit. We can measure that. But the main thing is what happens to the moon. And this is a theory that's been well verified. And that's really important. And even Einstein's theory of general theory of relativity hasn't changed anything that Sir Isaac Newton developed. It is extremely well verified. All right? We know that it's a very good theory. We're still humble about it, though. As Sir Isaac Newton would want us to be. But so far we keep testing it, and so far it stands up to every test that we can throw at it. Now, I want to give you an example of satellites orbiting Earth as a way of bringing together or synthesizing this idea of universal gravitation and the idea of centripetal force. Okay? Now, we developed this idea of centripetal force by thinking about a car on a circular racetrack, but it applies to moons, planets on circular orbits, and on any other orbit, really. But circular orbits are easier to work with. So, for example, we're going to think about objects orbiting Earth. Okay, so Earth is going to have the symbol, the mass of Earth, the symbol capital M, and the mass of the satellite, whatever it happens to be, like a weather satellite or something, M subscript S, lowercase m subscript S, the mass of the satellite. So, NASA puts a lot of satellites up. And so, it might want a satellite at a certain distance. This space station is up there at a certain altitude, certain distance from the center of the Earth. And to get it up there, they've got to have the right size rockets. If you have a really small satellite, you can get up there with a modest rocket. But if you want to get something up there big, like a piece of the space station, you have to have big rockets. So they got to design the rockets the right size, right? Now, if you're in a circular orbit, you can go into an elliptical orbit if you want. But if you're in a circular orbit, do you have a question? That was a fake out? Okay. If you're in a circular orbit, you can use the centripetal force formula as well. All right, so here's what that looks like. All right. On the left is gravitation, and on the right is F equals ma. The ma, when the A is centripetal force or centripetal acceleration, and the m is the mass of the satellite. Right? So here's gravity, and over here, there is MA. Right? So Sir Isaac Newton said, this will work. This explains what the moons of Jupiter and Saturn are doing. It explains what the moon is doing. It explains tides that are, basically, the water on the near side of the Earth is in free fall towards the moon, and it just does a little bit better than the Earth itself does. And so we get a big bump of water right up, pretty much right underneath the moon. Right? Now, let's get those bubbles out of the way. Now, let's cancel M subscript S. And this is the cool part. None of this depends, none of these accelerations and stuff that we're going to work on, none of it depends on how big the satellite is. Right? And now, if you're talking about something the size of a moon or something, then you got to be careful. But for man-made satellites, that thing cancels right out. Right? So here's a cleaned up version. So capital G, by the way, that's Newton's gravitational constant. All right? And you can read about that in MiniChapter G. So we've canceled out M subscript S. So so basically what I'm trying to tell you is this equation here is going to work for any size satellite, whether it's a little teeny Sputnik, 2 feet across, or some big school bus sized spy satellite. It's got a big job to do. And this equation still works. Now, if you look at it, you can see that we got r squared on the left in the denominator, and we got an r on the right in the denominator. So this one, you're going to get some cancellation. Right, here we go. Cancel 1 from the bottom of the left, and the only r you have on the bottom of the right. And on the right, you just have v squared left. And on the left, you have gm over r. Okay, so basically we've canceled r. So now let me park that up here in the middle. All right. And this, my wonderful students, is kind of a key equation for NASA and those guys, because it tells you, it relates the orbital size, r, that's basically your orbital size, and orbital speed, v. All right, so if you know the radius r of your orbit, you can figure out the required v and design your rockets appropriately. I mean, you don't want to have rockets that are too big. You don't want them to be too small. And if they're too big, you're going to waste rocket fuel. You're going to waste, a lot of energy. If they're too small, then you don't get up to the altitude you need. You're toast. Right? So now this is like an example of a spy satellite. You want to keep your altitude just close enough that your telescope, aimed not out at the universe, but down at the Russians' backyard, can keep an eye on what the Ruskies are doing. So the Hubble Space Telescope, they got about a dozen of those babies probably looking down the Russians' back pocket, and the Chinese and everybody else. All right, so to figure out, if you know the altitude you want, you've got to design your orbital rockets and stuff and get the required speed v, and produce that with your rockets. Now, another example, the opposite is if you need a certain orbital speed so that you can figure out the required altitude and r. So for an example of this is, say that you want your satellite fast enough to orbit Earth in once per day. Right? So in other words, an orbital period of 24 hours. Right? So what that means is, as the Earth spins, the satellite is also orbiting. And so it appears to stand at one point in the sky if it's right over the equator. And those are called geosynchronous satellites. Right? And we have to use this equation. gm over r equals v squared to design that. If we know the speed, we got to put it at a certain orbit. That's the geosynchronous orbit. All the communication satellites, that run cable TV and, long distance and all that stuff. Like when you see, on the evening news or Channel 9 Eyewitness News, and they're talking to somebody in Tokyo or, over in Korea at the Olympics, and there's a time to, so somebody in New York says, well, Johnny, how did that ice skater do? Well, Bob, it was like this. There's always a time delay, and that's because it's going up to the satellite and back down, and then back up to the satellite with a reply and back down to New York. So, geosynchronous satellite. Anytime you hear that delay from somebody in Korea and somebody in New York, that's what it is. All right? And so this is an example of how knowing the law of universal gravitation and a little bit about centripetal acceleration can get you some important information. How and where to put your satellites. Spy satellites or any other satellite. Space station, there's a reason the space station is at the altitude that it is. They want, such and such an orbital speed, and that means they have to have such and such an altitude above the surface of the Earth. There's basically such and such a distance from the center of the Earth, the center of mass of the Earth. All right? So here's our law of universal gravitation again. And make sure you make a note that this is an inverse r squared force. Now, I want to go through an important aspect of inverse r squared forces. Another thing about them is it proves that planets will orbit on elliptical orbits. They won't necessarily be circular, but they will be elliptical. The guy that figured that out, the guy that saw that in his numbers and measurements was a guy named Johannes Kepler. The guy that proved why that was so was Sir Isaac Newton. And Edmund Halley is the friend of Newton that applied that to comets. He knew that the planets orbit the sun on ellipses, a set of famous laws of motion for planets. The equal areas for equal times law, that's what this diagram is. You can look it up in the textbook. Average orbital distance to the third power is proportional to the orbital period. Here's Sir Isaac Newton's version of that. There's a whole bunch of constants in there. The universal gravitation constant, G, the sum of the masses of the two objects, and the average orbital distance, A, to the third power. And so Edmund Halley knew all that. Sir Isaac Newton had proved it. So Edmund Halley decided, let's apply that to comets. And he said, if that's really true of planets, which he was confident, and Sir Isaac Newton was confident that it was, he said it should apply to comets because they're moving on highly elliptical orbits. Most of the planets are fairly circular orbits, but comets. So what he did was he looked through history at the records of observations of comets, and what he found was this. Go ahead and write down these dates. 1531, a comet. And they saw a comet in 1607. And that's the time of William Shakespeare. 1531, that's the time of King Henry VIII, Thomas More. 1607, Shakespeare's time. 1682, I don't know what was happening. That's Sir Isaac Newton's time. And Halley, they were both alive. And he said that those weren't three separate comets. He said these three are the same comet, and he predicted that they would return that this comet was one comet, and that it's coming back in 1758. They could predict eclipses. You know, that was fairly easy to predict. You know, we could see eclipses and, you know, pretty much, you know, predict where they were going to happen. And he's the one that said, I think you can predict comets. And this comet, he said, is going to return in 1758. And by God, it did return. Just about Christmas time. 1758. Now, at that time, in that year, Sir Isaac Newton and Edmund Halley had both passed away for several years. But the comet did just what Halley predicted, and it is counted as a huge verification of Newton's theory of universal gravitation. So, and notice that these both of these guys had really cool hairdos. And look at that. I mean, there's no rock star on this planet ever who's had hair like that. Anyway, so this is a huge verification. And my wonderful students, make a note of this. It is an important property of the scientific enterprise that you must be able to make predictions that can be verified or falsified. You've got to predict something that could go either way. You know, it's got to be something that might not happen, but you're predicting it does happen, and you should be able to tell the difference. And if your prediction is good, then that means your theory is nice. Okay? Now, we're going to dismiss now. There's going to be a good-sized homework over the weekend. We got a lot of homeworking to do. I'll try to get it activated by lunchtime tomorrow. Be alert. It'll be due on Tuesday. You're dismissed.